Yeah, yeah.
Okay, sorry everyone for the delay, a lot of technical issues. So we'll have Khandokar and the Nayem giving his final internship presentation. He's a PhD student at Indiana University of Bloomington, and he will give us a very interesting talk about speech quality enhancement for not only noise suppression, but all kinds of other artifacts. So with that, the floor is yours, Nayem.
Share my screen. I hope everyone can see my presentation, right?
Yes.
Yes.
Yeah. Thank you. Okay. Good morning, everyone. So, as Sebastian is saying, my name is Khandokar Nayem, and today I will present my final presentation of my this summer internship with Microsoft Audio and Acoustic Research Group. So, my research topic or the project was unified speech enhancement approach for speech degradation and noise suppression. So over the whole presentation, I will talk about what are the approaches we took and like why we took that and what we learned and what are the future approaches we can do. And my mentor was Sebastian Braun, and let's go ahead and start the presentation then. And before starting my presentation and talking about the project, just a little bit about me. So I'm a PhD candidate at Indiana University as Bloomington, Indiana. And if anyone doesn't know where the Indiana is, it's just in the middle of nowhere, like in the Midwest. And but originally I'm from Bangladesh. And at the bottom, I want to show the map in the where my country is because most of the people doesn't know like where Bangladesh is. Sometimes they thought it is part of China or India, but it's just a tiny bit country, just besides India and besides Myanmar and just under China. And it's a very tiny country. It's just because this small equation is just how small our country is compared to California. So it's actually quite one third of California. And in my PhD, my advisor is Professor Donald Williamson. And my dissertation topic in my PhD is also on enhancing speech in various noisy environment that can assist hearing aid and voice assistive technologies. And with additional focus, I give on producing perceptually present audio. And currently, actually, I am staying at California Irvine. And after this internship, I plan to go on a short trip just to go around few more states. And these blue states are already the state I already visited. Maybe I will count add some more. Okay, so enough about me. So let's start with the topic we are talking about. So first, we are talking about developing a unified speech enhancement. So first, I want to talk about what is the traditional speech enhancement looks like. So the basic form of speech enhancement model is removing additive kind of noises. So for example, a common like scenario can be in a restaurant where lots of people are talking. Maybe I am there with my friends. We are talking also. There's music, television is going on. So lots of another sound sources are all around us. So if we capture the sound with a microphone, so maybe it can be a single microphone for single channel audio. So there will be lots of noises, and we generally like say that as additive noise because these are the uh, other sound sources created sound, and it can comes from like people's talking, kind of babble noise or cafeteria noise or water running noise. And also it there will be some kind of reverberation because of the size of the room and depending on the environmental quality. So there's some kind of additive noise would be added with our speech. So the basic form of speech enhancement basically removes these kind of noises and gives you the clean version of two-person talking or maybe different things. But besides these traditional speech enhancement approaches, so there is also like currently new distortion or degradation, we have to focus. So we call it like a speech degradation. So in this degradation criteria, we can mention like a 4 different kind of distortion, which is a kind of different from additive noises, because additive noise actually comes from different sound sources, whereas this degradation actually forms from the signal degradation because of the microphone we can use. If the microphone is not good enough or not have long like bandwidth range, there can be different kind of distortion can be happening. So here we are not for major kind of speech degradation. So one is codec distortion is quite common when we compress the speech using a loosey codec, maybe with a very low bit rate, because it will create a very small audio file and it can create like audible artifact. So for example, if we use a very low bit rate MP3 or GSM kind of codec uh, compression, then this kind of distortion can happen. Also, we can see the clipping kind of distortion where speech signal is too close to the microphone, so too close to the mouth, and like maybe the sound of the speaker cross the dynamic range of the microphone, then we can see the clipping kind of effect. And also with a bandwidth limitation, maybe we are recording the audio with a very low sample rate devices. So maybe 4 kilohertz or even 8 kilohertz, where we can nowadays it's quite common to use like greater sampling rate devices, maybe 16 kilohertz or maybe higher for studio quality audio. And there also can be gaps in the audio, which is quite common if the audio is passed through in telecommunication through poor network condition. So maybe there's a few packet of speech are missing and there will be jitter in as a result. So there will be no speech construction on the receiver end. So this kind of gaps can also happen. So this kind of speech degradation, how can we tackle that? That was like a one motivation and goal of this project. So in here, just to give a feel like how serious or how bad the noise can be or degradation can be. So here is an example I show before playing. Like this is the clean or input version of this speech, and you can see like these three are like three different distortion if we apply. So these are all like synthetically applied distortion. So you can see like if we apply GSM uh, codec distortion, which is quality 3, which is quite low. You can see like if we look into the time domain, it's quite similar, but you can see in the spectrogram that there is a high frequency component are also missing. In the clipping, you can see like all the values are kind of clipped to the top, and in the bandwidth limitation, you can quite see like all the frequency greater than I think 2.5 thousand are actually all are gone. So it would be like a very low single sound. So just to hear how the degradation looks like. So this is the clean or non-distorted audio.
Held on their wide shelves a large number of uniformly bound books. These furnishings followed the contours of the room, their lower parts leading to huge.
So this is the clean one, and if we apply codec distortion,
Held on their wide shelves a large number of uniformly bound books. These furnishings followed the contours of the room, their lower parts leading to huge.
so you can see like that's quite a heavy distortion there. And this, if we apply clipping on the audio,
Held on their wide shelves a large number of uniformly bound books. These furnishings followed the contours of the room, their lower parts leading to huge.
yeah, sorry that all the values are too high. And if we have like a bandwidth limitation, so it would be something like that.
Held on their wide shelves a large number of uniformly bound books. These furnishings followed the contours of the room, their lower parts leading to huge.
Yeah, it seems clean, but all the high frequency values are gone. So from this point of view, so what is our goal in this project we have in this summer? So we want to build a speech enhancement system that will repair this audio degradation, such as this clipping, lost bandwidth, and codec distortion. Also, we want to investigate like if we can propose some small model that can be like runnable or trackable this repairment in real-time processing. If we also investigate like the modular sequential processing kind of approach, because that would be beneficial because we can swap different module depending on the distortion are happening or how stable the model is or the whole network is. And also like we want to evaluate the model performance on real recording, which we'll talk about there, because getting real recording with this distortion and specific distortion with quite bit difficulty for our findings. So we will talk about that, how we can evaluate and how we did that. Okay, so from this goaling standpoint, so before to familiarize with what we did, I just want to mention like a few notable work. They actually helped us to achieve our project goal. So first, because we are uh, trying to build a unified system which will tackle both additional noise or additive noise and also this signal distortion, we actually need a good like a model that can handle additive noises. So for that, we actually adapt the cruise model, which is proposed by Sebastian in 2021, and it is really works really well with a deep noise suppression kind of approach, and it's just a conventional encoder decoder kind of style with a glue kind of RNA in the cell, and it really good performance gain we saw in real time scenario. And then there's a few work with the bandwidth extension. So recently the notable work people try with wave unit that was proposed by Spotify, and also in the MSR people use speech super resolution. And recently Adobe actually proposed quite a few model, the GAN model, this call it Hi-Fi GAN, Hi-Fi GAN 1, Hi-Fi GAN 2, and bandwidth extension, all they need. So these are the few band extension model. They actually try to expand the bandwidth with a 4x kind of environment. And then with removing this kind of speech degradation, like a clipping codec and gaps kind of, there's quite a few paper actually work on this task. So notably, there's a unit kind of structure, and also recently we have a Dolby proposed universe kind of paper where they actually try to solve a wide different range of distortion. They said it is a 55 different distortion type, but I think they are synthetically generalized this kind of distortion. And lastly, there is a recent paper by Google in 2020 where they try to do bandwidth extension in real time, which is really good, is because when we see the performance in the bandwidth extension is generating new like a values where there is no value, as you can see from the cutoff. So doing something real time in the bandwidth extension task was really good, and the model was performed quite nicely on that. But this paper actually tried to do bandwidth extension until 16 kilohertz, whereas this Hi-Fi GAN, which are offline, of course, they try to expand the bandwidth until like 44.1 kilohertz. So yeah, because that's not real time, that can maybe applicable. So yeah, so these are the main notable work we can see in there. So to go to our task, so because as we say, like there's a lots of degradation are happening, like codec clipping and band extension. So how we can train a model to learn this kind of artifact? So for that we need a good data augmentation and generating this kind of degradation when the model is training. So for that, we use like a degradation specific augmentation, where we mention the codec clipping and bandwidth extension, and we use like a quite a different kind of library, so that we know like we can generate generalized kind of degradation, which is available in the quite close to the real world scenario, kind of like that. So for example, like for the codec, we use the Spotify Pedalbot proposed like MP3 and GSM codec, and for the MP3, like they have like a quite flexible function. They have, we can use like a variable bitrate from any value from 0 to 9, and it can be float level also, but we try with just integer level 0 to 9. And then we have the GSM encoding where we can use like a different quality of the encoding. So 0 is the highest quality or good quality, and 3 is the lowest one. And also that's with the uh, MP3 also. So 0 is the best quality audio with the MP3, and 9 is the worst quality. And then we have the clipping augmentation. So we have two different kind of augmentation, where one we use like a nonlinear distortion kind of sigmoid and rectifier function, and then also we use Spotify proposed guitar effect kind of clipping effect. uh, then we can see in the bandwidth extension we actually use a different kind of low pass filter. We use a butterworth filter with a range of 500 to 400,000 kilohertz range low pass filter with a high order. And then we also use Spotify one with a very soft low pass filter. And then for the extreme case, we use like a FFT filter where we go to the spectrogram and cut out all the frequency from any frequency value from 500 to 4,000. So one thing we have to show, like we do not do any inherent resampling, and model is not limited to fixed sampling rate. So what does we mean by that? Like most of the approaches in the bandwidth extension, they take the input and they actually resample the taken input audio to the desired level. So, but that is a problem because when we do that, the model actually have a like fixed range, like this should be the desired sampling rate taken as an input for the audio of the model. So we can remove that part. So that means when we give a audio input in the model, we actually upsample the audio until whatever the level we want to, and then just feed the audio into our model. So we feel like that would be the much more generalization version of the model, rather than using a like a upsampling layer inside the model itself. And one other thing, if you can see there, we actually mention about 3 degradation augmentation, no gaps in here. It's just because for this project, we actually exclude gaps for now. It's just because this packet loss concealment is actually happen on the receiver side of the end, whereas we try to do our enhancement algorithm module like deployed into the sender side of the uh, model. So at the speech is recorded. So that's why for now case we actually do not include the gaps, distortion, or augmentation in our training. And so these three are just the degradation or speech degradation we talked about. But other than that, for generalization, we also use like quite a few other kind of augmentation for the generalization case. So we use like a spectral augmentation, like 80% times or with a random value. We use like a pitch augmentation. We use reverberation, and we also use SNR augmentation using a normalization like a Gaussian function with a 5 to 10 dB like normal function, and also we use level augmentation with a minus 26 to 10. So in the bottom, we are showing like a general overview, the data augmentation we imposed in our model. So all the data augmentation we applied on the audio, they are running on the real time, so on fly. So that means like every time we take a speech signal and we take a noise from the dataset, we cut a specific piece of the speech and noise, and we pass through this different augmentation module. In here, the red arrow mentioned that like the noise are processed separately, and the black arrow means the clean version of the speech signal is processed separately. And you can see like we pass through speech and noise to the spectral augmentation, then we apply pitch augmentation both of speech and noise. And after applying pitch augmentation, we apply reverb, and this outputs the target speech, which is the target of our model. Then after the reverberation, we apply sound augmentation, bandwidth augmentation, clipping augmentation, level augmentation, and codec. And after that, finally, we get highly augmented or noisy version of the speech as the input of our model. And you can see like after the speech augmentation, this this red noise actually blend with the speech. So that means from SNR augmentation, actually speech or clean speech and noise are actually mixed together, and all these augmentation are applied on noisy speech. So these are actually applied on noisy speech audio. So that's our input in our model, and that is our target of our model. So both are actually right now in speech wave format. So these are the augmentation we applied. And so after this data, so now we talk about the model we use. So as we mentioned before, we use this cruise network as our baseline model. So here we are showing a generalized view of a cruise network. So cruise network can see, like as I mentioned, like have a like a encoder and decoder value, and here we use like a 4 encoder decoder with a bottleneck in the middle, where we flatten the input uh, vector into like a few parallel recurrent layer. Here we use like a 4. We will, so that is our baseline structure. And in the bottom, you can see the block diagram at how the model actually gone. As you can see from the previous slide, we process the speech and noise, and after the augmentation, we have the inputted noisy audio and also the target audio in the wave format. Then we pass into the model where we apply the STFT. Then we extract the feature in the compressed format. Then we apply this feature into our cruise network. So the output or target of the cruise network can be both a complex filter, or it can be compressed spectrogram. So depending on the target we have, we take the output from the model, and lastly we apply the inverse STFT to get our enhanced speech audio. So this cruise model have like a fixed receptive field like 80 millisecond, and the RNN is inside depending on how much receptive field we want with the RNN. And then we apply 20 millisecond look ahead because of the overlap and add. So basically 20 millisecond is all the time we need to run it in a real time. So 20 millisecond actually is the lag time we have for processing. So as we mentioned before, cruise network is a real-time inference model. It really gives a really good performance in noise suppression task. So besides this cruise model, we also use another model which is called CNET, which is actually stand for speech enhancement uh, model. And here we can see the block diagram of the big network. So basically it is just a like a unit kind of structure where we have this encoder module and the decoder module, which are wrapped inside like two sandwich between two convolutional layer. And we can see like there's a skip connection in between there. So this is the full network is actually just convolutional network. And this model has like comes with a different version or model, but for our task, because our main focus is on like inferring the audio in real time, so with the model we choose is a streaming audio streaming model. They say it as CNN is streaming, but we mean or that is casual. So in this whole slide, wherever we are mentioning CNET, actually that is actually a streaming version of the model we're using here. So about the receptive field, so we have like a 42 millisecond receptive field with CNET, and it has like a 16 millisecond look ahead. So you can see like there is 4 millisecond less we need with the CNET model. So it also do the real time inference as we mentioned. And lastly, there is a proposed like a model can do like a bandwidth extension task in real time. Oh, and one thing I didn't say explicitly, but I'm to say that the input is time domain wave audio and the output is wave audio also. So that means they actually do the whole processing in the time domain, the CNET times. Okay, so now we know the CruiseNet and the CNET a bit. So what we try to do in this project. So in this project, we try to propose a model, which is a cascade kind of model where we propose a noise suppression module, which where we will deal with this denoising and reverberation, and then we want to propose a like a speech degradation module where we repair this codec distortion, declipping, and also the bandwidth extension. So this modular version, we want to use that one instead of using a whole big model where we do the whole task. So the main reason we are trying to do that because this modular uh, model has a like a advantage of switching of module whenever we want to, depending on the capability of the system we are using or the network capability. So different factor can influence us to switching of different module if we want to, and we can repurpose a different module for different application. For example, like if any system or application is susceptible to one specific kind of distortion, we can swap the module with just only that distortion only, giving the easier or shorter model in the deployment. So with this same model architecture, so this enhancement model can um, inference both a filter or signal estimation, and also this different loss function. We want to optimize which with loss function works better with different types loss. So as we say for the speech degradation or SD module, we try this both CruiseNet and the CNet, whichever works better. And mostly for the noise suppression, we actually use the C CruiseNet basically because they in our experiment it gives the better result uh, mostly all of the time. And about the loss function, so we use a compressed complex MEC loss function where we can see in the here. So I don't want to explain that. So it's just a very straightforward. We just compute the complex MEC loss and we actually compress that with some factor C here. And we also experiment with a complex ME weight loss. So complex a mean absolute error loss. Also we try with that one, but all the results we show here are actually with CMEC loss because that are giving us a better result than the complex ME loss. And then the dataset we use and the evaluation metric we use for evaluating our model and our approaches. So, so training dataset actually is a big part of this learning this speech enhancement algorithm. So in here we say like we kind of have a two quality kind of audio training dataset we have. So on the one hand, we have a large scale consumer quality audio like LibriVox, ABS, Spanish, kind of like more than 800 hours audio. So they are consumer quality. That means they are not fully or 100% clean or strictly clean like studio quality audio, but they are greatly available to use. And then on the other hand, we have the studio quality audio, which is this TK, MS Phrase or TAPS dataset, which has kind of 100 hours kind of audio. So we tried with like both dataset, and we find that like using consumer quality audio, but greater volume yields a better result. So this is the dataset we use for our training the models. Then for the test dataset, so finding a real-time audio is kind of challenging because our goal is to produce the model so that it performs very nicely in the real recording kind of settings. So in here, we basically choose two option in here. One is interspeech 2021, which is the third DNS challenge test dataset, which is it contains like around 600 files. And also we use like a Niska test dataset where we have both simulated and real recording audio. In here, we use like a three subset of this test dataset, where this four is forensic test dataset, which is simulated audio, and also P501 is also simulated audio, but the live talk actually real recording. And we have like around 712 file, which is in total gives us 1312 file, which we use for test dataset for evaluating our full model. And now how we evaluate the model, because as we say that our goal is to achieve good performance in both noise suppression and also with other kind of degradation. The thing is there is no explicit uh, um, explicit more evaluation metrics for this speech degradation. So we actually try to use both, and yeah, try to make a sense which evaluation matrix contributes to which one. So on the one hand, we use this DNS MOS, which is a P835 protocol with uh, MC, M back, and M overall metric. And on the other hand, we use this Niskia paper proposed matrix, which gives us the MOS score. And also this gives us four different score with noisiness, discontinuity, coloration, and loudness. So one thing we want to use is in our evaluation matrix, because our main focus is on real recording audio, and our test set also mostly have that. So we try to use the non-intrusive or non-reference kind of evaluation matrix, where we use these things. For the Niskia one, I want to elaborate if you are not familiar with Niska model. So Niska basically actually already trained model. The goal is the model is to output the kind of uh, human kind of preference with audio. So it gives us a MOS score in different criteria. So this MOS actually is the regular MOS, mean opinion score, we can get from a speech quality. And about the noisiness, discontinuity, coloration, and loudness. So they are kind of not cut and forth which thing they want to explore. So I just want to mention they actually observe quite few things. For the noisiness, it actually observes if the speech is contaminated, or if there's additive kind of noise is there, this kind of thing. Also with discontinuity, it actually observes if audio is cut off suddenly, or there's interruption in there, or there's kind of any artificial artifact in there. And on the other hand, the coloration actually uh, more like a directness or brightness. So in audio, I'm not sure how that mess up, but it's a try to do that kind of directness and brightness in audio kind of sense. So if we try to match up our degradation, speech degradation with this matrix, you can have a kind of loosely sense that this coloration, because this coloration contributes more with a bandwidth limitation kind of thing. If there is a more bandwidth is actually cut off from the audio, the coloration value most likely to influence or affect there. And also for the discontinuity, if the codec artifact is happening there, we tend to have a lowest score in the discontinuity. Similarly, in the noisiness, you can see the additive noise contributes to there. So, but again, one thing this relationship is not very linear. It's a very non-linear kind of relationship. So that means not only uh, bandwidth extension, so sorry, bandwidth limitation affects the coloration, clipping also affect, additive noise also affects. So all other things also affect. So it's kind of not clear which metrics are best for identifying codec distortion or identifying clipping distortion for that one. Okay, so being that thing in mind, so one important thing is we do not train our model with on this metric. So we just want to just evaluate at the inference level how good or bad our model is. And about this DNS MOS metric, we do not basically use this AM overall. It's just because AM overall actually is a linear function of MSeq and MBAC, which are actually proposed for noise suppression task. So for because additive noise removal, we actually look into just MSeq and MBAC score, but as a separately. But I think looking into the overall score is not a very representative for our scenario. So that's why for representing the result, we just like remove this m overall from our results. Okay, so I think you guys have like a loose idea of what we are doing. So now we're to show like what we get from our result. So in here, like we are like trying to do this speech degradation task in a few separate way. So in here, we are showing like we try to do this speech degradation kind of removal with uh, approximating mask versus spectrum approximation. So in here, we try to focus just on speech degradation module, which is can be applied after the noise suppression task. And here we try to do with either we do mask estimation or spectrum approximation. So just to clarify the model or the chart we are showing here. So in here, we have actually six score we are showing here. So all the NISCA metrics, the MOS, noisiness, discontinuity, coloration, and loudness, and the DNS MOS value of MSIG. We are not showing the MBAC because that task is here just to speech degradation removal, so not noise suppression. That's why the background noise value we are not showing in here. So about the model we are comparing here. So we are using the cruise network in all this model we are showing, and we apply this codec distortion on the model, and we compare how that works with if we estimate mask or complex mask, or we estimate the signal estimation. So in here, we are doing on the codec, on the clipping, and for the bandwidth extension, because we want to like produce new score for the bandwidth. So in here, applying mask is not helpful or will not work basically, because it just multiply the zero value with some large value, which is of course would yield zero still. So that's why we just want to show the score of bandwidth extension with a signal approximation, which is the orange in here. And then we have if we apply all these distortion with a codec clipping and bandwidth extension task as a whole, and apply the mask as a final target or as a signal approximation, which are the gray and the purple in here. Okay, so all these all these uh, 7 model are trained with almost no additive noise. So because our goal is to just to see the performance on speech degradation removal, so that's why we do not remove, sorry, we do not add any strong additive noise, just a soft additive noise with using a like a Gaussian function with 45 to 5 decibel. Yeah, it's just because whenever if we use a noise suppression module at the front, actually there will be remain some noise at least. So that's why for the robustness we actually use that. So for the task here is it can remove single distortion, where this is a codec clipping bandwidth extension, or these two model it try to remove all the speech degradation we are talking about. So as we mentioned again, the test dataset is interspeech and NISCA, and for the loss function, we use this complete MC loss function. And if we just to look into the chart we are showing in here, you can see like these two are for codec, and you can see like the if we look into the MOS score, so the signal approximation tends to get a good result compared to the mask one in the MOS. And because these two model are for the codec, and we see that the discontinuity most likely is the better indication of whether the codec artifact is removing or not. And you can see here also this mask version is performing a bit low than the signal approximation. So from that look seems like for the codec task, signal approximation is the better one. And if you look into this clipping task, so where is the light blue is the mask version of the clipping, and the green version is the signal approximation of the clipping. So they are kind of tie to tie is just because when you look into the mask, this mask has the better value, but in the coloration, mask has slight close to this one, but in the loudness it also has value. But in the MSeq, like which is the signal quality, the noise suppression task, you can see like the signal estimation yields better result. So I think like maybe both are quite good, or maybe one is kind of better than that one. And lastly, so the bandwidth extension, we do not have any that many comparison because it's just a single estimation task. But we can see one thing, that the MOS score is quite low. So which we'll talk about later in the part of the slide. So that indicates that for removing this bandwidth extension, cruise model is not that much capable from the look of this score of the MOS, and also with the correlation, the score is quite low. And then if we compare with the overall distortion, with all distortion with the mask and signal approximation, you can see here the purple one is the signal approximation and the gray one is the mask one. So you can see like the signal approximation yields a quite good score at a while. Uh, and it's maybe one reason is because we are actually using this bandwidth extension, and as we say before, bandwidth extension is not possible with mask model. So that's why purple is what giving good result. And one other thing I forgot to mention with this red line. So this red dotted line I show in the charts are for the matrix for the input signal. So that means the input signal have this higher score compared to others. So it's kind of interesting like that. The input have greater score compared to after we apply this pass through this speech distortion module. So you can see like other than this MOS and MC, almost all the time the input signal have the greater score, which is should be the greater value. So that's one interesting observation we have. So okay, so now we're familiar with the mask versus direct signal approximation. Then we try to build our speech distortion module, which we mentioned by ST module. So in here, we took from the previous slide, we take the best learning module in here. So in here, we try to train a model just for speech degradation task. But in here, we are showing that if we use this cruise signal approximation model, this is the navy blue one, and we're comparing with all this signal approximation. So this is the codec, this is the clipping, and this one is the value extension. And these two model are working with removing all the distortion altogether. So again, so the purple one is the cruise model with try to remove codec, clipping, and bandwidth extension. And the green model actually is the CNET model, which try to do the same task. So one difference is that this cruise model are working in the signal approximation or time frequency domain, you can say, but in the CNET, they actually do all the processing in the real-time environment. Okay, so again, the training procedure is kind of similar here also, like there is almost no additive noise added for training this network, and we try to remove this speech degradation from the audio in here, and same loss function is used here. Okay, so if we analyze the score in here also, this MOS score, you can see like these two model are our main concern, because these two module trickle to remove the main distortion. You can see this signal approximation yields a better result than the CNET structure. And if you can see also in the noisiness, like this one is way better than this CNET one. But interestingly, in the continuity, coloration, loudness, and MSeq, this CNET tends to perform good. And one important thing is like that coloration stands for bandwidth extension task. And here, like after the codec, like a CNET works really good. So our focus is like that CNET might be a good model for speech distortion removal task. And from that point of view, we try to explore which one works better, either is the CruiseNet or the CNET. And before going to the next slide, again, I want to mention that the red line is the inputted level of the audio. And here you can also see the same trend that the MOS and the MC, all the score generated from the model are quite low. So that's interesting here again. Okay, so we separately talked about the speech degradation model. So we want to do a unified or single task. So that means we want to remove all the noises from the audio. So from their perspective, we are trying to do two different approaches. One is end-to-end approach. End-to-end approach where we try to build less big single model, which try to remove both additive noise and also the speech distortion. So in here, we actually proposed like or try with four different sized network, which is the cruise small, cruise medium, cruise large, and also the CNET network here. So first three model are the model where we try to do this end-to-end task. So compare what is the difference between this model. So cruise small, medium, and large is basically the size of the network and the filter size we use for the uh, model we have. Like for the cruise small, we have the filter size of 32 uh, with the starting with 64, 64, and 64 with four parallel RN cell in the middle. So for the medium size, we actually uh, enlarge the uh, value of this filter with a 128 with again RNN 4 parallel score. And then we have the cruise large where we actually every time we multiply is 2 times with a single RNN1. And actually in the original cruise paper, it shows that if we use a single RNN instead of 4 parallel cutoff structure, that would perform better. But it comes with the complexity with using a single RNN network. And just to mention here how much or how big the complexity can be, you can see like we mentioned the complexity of this network with the max score. So in the max value, you can see the whose small have like a parameter like a 2.7 million, whereas the medium one has like a more than double, like 6.2 million, whereas the large one just with a single RNN and just 2 times filter size, it has 36.7 million. So that is like a way big kind of model than this small and medium sized cruise. And interesting, the CNET, the CNET network we use in here, so it gives a very small um, complexity with a 4.9 million, which is bigger than cruise small, but still small than cruise medium network. Okay, so first we want to first compare like this four model in like all the metrics in here. And again, because we are trying to do a unified task, so that means so we are trying to do this speech noise removal also. So in here we are also showing the back back score in here. Okay, so because our focus in on fast four models, as you can see, definitely this cruise large one yields way better score than this other three. But the thing is like the complexity is two of the large than applying in a model. So after, other than this cruise large network, you can definitely see like CNET gives us good score in the MOS, and in here the medium is scoring better than the CNET one, but not too much a big difference in there also. And every time in the background noise, you can see like we can see get a score in the CNET. So from this fast look, we can see like a CNET network is perform quite nicely compared to the a small network it use, and it of course uses like a large network than the cruise small, but a small network than the cruise medium. So this is the performance of our end-to-end approach. But then we want to explore, okay, so if we use a single network, okay, that can be good, but you can't separate the module with a noise suppression and speech degradation removal module. So then we focus on like what happen if we use a cascade kind of structure. So last four module where we try to do in a cascade style. So that means we have two network. At first we have this noise suppression module where we use a cruise small network, and we use this pre-trained cruise network to do the training for speech degradation module. So we put that cruise small module in a inference mode or frozen, and then we train the speech degradation module later. So in here we have four different module. So at first we use the cruise network as a speech degradation model. Then we have CNET as a speech degradation model. And then we have two variation where we enforce codec distortion is the part of noise suppression and do the other task in there. So here we compare the scores at the same manner in here also. So these last four models are the score of these four cascade style or unified two-step modular version of the model. As you can see in here, this if we use this these two model, if we compare, so this one actually is that all cruise. That means noise suppression is of course. So we use noise suppression is cruise always. So then speech degradation is cruise and the scene. You can see the gray is quite outperform almost every time compared to the cruise net. So it shows us that if we try to do noise suppression task, so the speech if we try to do the speech degradation task, they actually seen it perform quite good when it just get the noise removal audio and try to do the signal degradation then. And then we try to use the other version where we enforce the codec as a part of noise suppression. In here also we can see like the green one, which is the CNET version. CNET version actually performs quite nicely compared to the cruise one, except for the mouse, which is quite tight to tight. But other than that, always the CNET actually performs better than the cruise one. And one thing again I want to mention, like this red line actually is the input of the signal, and this black dotted where actually so black dotted actually is the output of this noise suppression cruise small noise suppression task. So that means if we do not apply any like a speech degradation task, that would be the score or from just from the noise suppression. And surprisingly, you can see like if we do not use like any like a degradation speech degradation module, we could get better MOS score, like at least in here in the noisiness also, but not in the MC. You can see like MC quite low than the input. So that's interesting, like findings, because if we just use just only the noise suppression, does it better? Because the metric shows that if we do not use speech degradation module, that would be better. But I will play some sample. Like it seems like this sorry, it seems like this matrix is not like 100% like accurate for our task. That means like whether those scores are high, but that doesn't mean like they actually solves the problem. Like it doesn't mean it solves the problem of it do the bandwidth extension, or it solves the decode clipping or codec artifact removal. So that means this makes the question like what should be the good evaluation metrics for this task. So we don't have any good answer for that one, but we have to share like that this score is not always telling us the truth. Okay, so with that in mind, I want to show like what is the audio looks like for our test. Okay, so this is the single audio we want to show in here. So this is the input, and I will like pass through like a different model we applied. So let's first hear the input audio, so which is the noisy version of the audio. Okay, so So, and one thing, so these are the real recordings. So that means we are not added any artificial noise within here. So that's why it might seem much cleaner than the augmented audio we use generally. Okay, so here's the input.
In considerable detail. Northern liberals are the chief supporters of civil rights and integration. The social and psychological consequences of.
Okay, so this is the input one, and there's two ways we can do it. So if we apply dust directly this speech degradation module, like because you can see like there is like a big bandwidth gap in here. So this is the mod result we can get if we just apply this speech degradation module or CNET without any noise suppression. So here's the it looks. Oh,
In considerable detail. Northern liberals are the chief supporters of civil rights and integration. The social and psychological consequences of.
So there's quite a bit noise in the behind if you can listen to that. And our proposed approach is like that for the input, it should first pass through the noise suppression module, which is this one. And then after that, we will pass through this CNET speech degradation module, which will be that. And if you can look into the spectrogram, it is much more cleaner and much more structured than that this one. So let's listen through if we apply this noise suppression module on that.
In considerable detail. Northern liberals are the chief supporters of civil rights and integration. The social and psychological consequences of.
Yeah, so it's seems much cleaner than the input one. And if we apply the degradation module, then
In considerable detail. Northern liberals are the chief supporters of civil rights and integration. The social and psychological consequences of.
and this was the input. Let me.
In considerable detail. Northern liberals are the chief supporters of civil rights and integration. The social and psychological consequences of.
Yeah, you can see like because this audio have like a greater high frequency values, it sounds much more pitchy than this one. And this is the another example I use. So it seems like it has the problem with the clipping one. So this is the input, and if we apply through this pipeline we have, so this is the output we have, which is much more cleaner and better structured, because you can see like there's a few missing values in upper region of the value, but whereas this um, spectrogram has nice structure in the higher region. So let's listen to that.
Gli italiani di tecnologico come innovazione prima di tutti è stata quella del digitale terrestre e subito si è pensato che è stata fatta per la Confederation Cup in arrivo.
This is the process audio.
Gli italiani di tecnologico come innovazione prima di tutti è stata quella del digitale terrestre e subito si è pensato che è stata fatta per la Confederation Cup in arrivo.
To me, this one sounds better. I'm not sure whether you can listen to the difference. And okay, so now like what we find from this work. So from the compare with to a single end-to-end enhancement model with for the task of suppression and distortion removal task, we find like the unified cascade model achieves the better performance in a whole. And then we see like even though like this cruise small module have like a low complexity, but it performs really well in noise suppression task, and it can gives us real-time inference, which is really good. We should also see like the CNET, the streaming or casual model, outperform cruise model in the distortion removal task. So maybe the cruise small is actually too small to like infer this high frequency value, so that CNET was perform better. And lastly, we see like the cruise small model actually highly susceptible to overestimating the signal level, which sometimes arise the clipping problem, which might be a one reason where the cruise network is not doing perform as well as the CNET. And from that finding in mind, we'll mention like a future work what we can going forward from here. So in the future, as I mentioned, like the cruise network have some really weird like overestimating problem, and it sometimes do like a real random scaling. Like I don't want to play this one because it will like boost up the air. I think everyone's, but I can see like this is like have like a bandwidth limitation problem, and that if we apply cruise small, so for suddenly this scenario like it boost up quite a lot like a Cleveland problem. So that's one thing we need to focus why this is happening and how can we solve that. And also like we do not do that much of hyperparameter tuning for this model, so maybe define loss function, weighting, and learning rate could get better result than this one. And lastly, we have a want to do apply another module at the end, which will do the high fidelity modular hi-fi module, which will convert like inference audio into a studio quality, which would be much enriched quality in the audio and better quality in my. And with that saying, I have to conclude my presentation, and thank you everyone for your time. And for the audio team, I have an amazing time when I was in Redmond and also when I am in remote. And a special thanks to Sebastian for mentoring me and all my intern cohort for this memorable 3 months. And with that, man, feel free to ask you have any question. And yeah, that's me.
Right. Thank you, Nayem. Sorry for the delay and technical issues in the beginning. We'll have till the next talk coming up in 12 minutes, so maybe we can take 2-3 questions.
Yeah.
Any questions from the audience? So I can maybe start with one. So in the your results, you saw that the MOS scores were really improved over the input, right? And one, although if you go to the final cascaded model, there seemed to be an improvement for most of the metrics, but not for coloration. So what was coloration mostly representing again?
So the main contributor for coloration, I think the bandwidth extension, but also like as I mentioned, like clipping, I think is the second contributor in there, and then the other kind of noises in there. So yeah, like
it's very interesting that the noise suppression cruise model is actually able to improve the score, right? It's the black dashed line.
Yeah, that's really surprising. Like yes, like if we look into the score only, like the noise suppression yields way better score. Like you can do like these values are way off the roof compared to other one. So yeah, so that's really interesting. Like and also like sometimes like the input audio is have better score. Actually, not in here. That cascade actually is better than kind of always, but
Ivan has a question.
Have you tried other cost functions when training the neural network?
Yeah, so the cost function we use is the like a complex MSC loss function, but we also try with the complex absolute error loss, but we find that complex one is perform better. But we can play with like a few weighting factor, because we could try with like a different weighting factor like 0.3, 0.7 or something like that. But there I think we need to find some like optimal parameter, because from the experiment I saw like for the clipping the 0.3 works better, but on the other hand for bandwidth extension we find like the 0.7 works better. So there is there is a scope for parameter tuning in there, but overall like we use like this complex MSC loss with the 0.5 default parameter.
Okay, thank you.
So we've seen that it seems to be there seem to be large differences on which network architecture is suitable for which kind of distortions, right? The cruise model seems to work better for noise suppression and maybe also codec artifacts. CNET seems to work better for declipping and bandwidth extension. What's your opinion? Would you think it would make sense to even further separate that, like to have one module for each of those degradations separately, or you feel you can do some of those degradations jointly? Because there's also no guarantee that the network architecture is suitable for all doing all the same distortions. Maybe you also need a different loss function to treat distortions separately. What's your opinion on that?
So I think from the using like a separate module for every distortion would be definitely would perform better, but I think that would not be effective in a sense like we need like a quite a list of trained model or module for that one, and like I think eventually we have to group in some way, but which grouping we can do, that can be a like a way we should explore, like which distortion can CNET handle better. Like from our like observation, we can see like a bandwidth extension works really good with the CNET, even though like we know like the CNET is good, but it doesn't meet perfect. So there's way of a scope of improvement. And of course, depending on the module, like we can have like a separately part module in a sense, like depending on the system where this model is deployed, maybe bandwidth extension is the most commonly used distortion in there. So maybe in that scenario, maybe having a dedicated or much more focused on bandwidth extension module would be better compared to the other case. Like maybe for low recording or where the clipping happens more, maybe a clipping waiting. Like I think we should use like generalize the model for removing distortion, but we should do the grouping. But maybe we can tune the parameter depending on the distortion which is stable on the network on the system overall. I think that would be my take actually.
Okay, thank you. Any more questions? Otherwise, going once and twice. Nobody? Okay, then we'll have 5 minutes left to the next meeting. Let's thank Nayem again for his nice presentation.
Thank you.
And we have actually another intern presentation coming up in 5 minutes. So see you then.
Thanks, Nayem.
Thank you.
Thank you. Nice talk.